Hi, so this is a continuation of the previous video where we worked on data dimensionality, data dimensionality reduction techniques, reduction techniques. So what we did was discuss different methods of doing this, of reducing our data, and we have feature selection and feature extraction. So for this clip here, we'll be focusing on PCA principle component analysis. This is a type of feature extraction method, and here we focus on mainly the components of our data set. So we'll be focusing on feature reduction or feature extraction of our data set, and here we can visualize our data. We can also compress the data. For this model here, I've decided to focus on a plant data set. So this plant data set here, we have different works that were done on it to collect maybe different properties of this plant. And we have 23 features in this data set, and all these features basically are a description of this plant. 23 features, and we can use this 23 features or 23 components to determine if the plant is edible or it's poisonous. Now that we know we have this data set here with 23 features and we want to build our PCA, I'll jump straight into the Python model and see if we can do this. So the first thing we do is bring in our data, and to do that we'll use pandas. So let's just import pandas. Pandas as PD, right? And because this is a plant data set, let's call it P instead of typing our plant all the time. PDF, plant data file PDF. Okay, I think that'll work, and we'll read it PD dot read CSV, because I already have the data file here in the working folder I have, so it'll be plant CSV. So we'll read the CSV, bring it in, plant dot CSV, PDF PD dot read CSV, plant CSV, right? Now that we have our data file, what we'll do is we'll encode it from strings to integers, since we know most our ML models work with integers encoder. So we'll do this by using a standard encoder. So we'll label encoder, but remember we did not import it, so we'll come here and say from sklearn dot preprocessing import label encoder standard scalar. Sklearn pre-processing import label encoder standard scalar. Perfect. So now we have our encoder as label encoder, right? So after that we'll use let me just create a for loop to transform our data. So we can say for every column in a data file, for every column in the PD data file, in our data file, let's say columns, for every column in our data file, so then our data file will be equals to each column is equals to encoder from strings to integer, we fit transform, right? Fit transform all columns. P data file all columns. So we say for every column PD not all columns, PD column, encoder, fit transform all columns, right? Actually, let me import everything I'll be using so that I don't have to keep going back. Since we'll be plotting our data too, let's import mat plotting library dot py plot splt and plot library splt. Then, and since we'll be using PCA, let's say from sklearn, sklearn decomposition import PCA principal component answer decomposition import PCA. We can also bring in let me run this. We'll bring in everything else later, I guess. So now that we have transformed our data, let's bring in our features, all the columns in our features. We can say X. Now we're taking out our features from the data set, all X features. From each column, let's say P data file dot. So remember I mentioned that this data set has 23 features, right? So open them out, 23. And while label our data file dialog, 0. Okay. We used our standard encoder from strings to integers, and after we have it in the integers, now we transformed our data and brought out our features. So let's run it and see if we had any mistakes. Okay, it's not out of root. Okay, fit transform. Yeah, spelling mistake. Fit transform columns, data file columns. Perfect. Label encoder has no attribute. Fit transform. Why do I keep making mistakes here? Fit transform. It's P data file. Perfect. Now that we have our data this way, now we can start building our PCA. So we can say, actually, let's scale our data. Let's start by scaling. This is not necessary, but it might affect our PCA. So let's use a scaler, standard scaler, standard scaler. Scale our features. X features is equals to scaler dot fit transform X features scaler, standard scaler, X features scaler dot fit transform X features. Okay, perfect. Now that we've scaled it, let's try. So the first thing we'll do before jumping to our PCA, the first thing we'll do is we'll check how much each component contributes to the overall model. So we'll say PCA is equal to PCA. So to check this, we'll check what's known as variance. PCA.fit transform. X features. We have our features. So to check the variance, so that is the amount of information each feature contributes to our model, we'll start by the variable called variance. Check variance. That's equals to PCA dot explained variance. PCA variance, PCA dot explained variance. Okay. Now let's plot this. PLT. We'll use a bar plot just to see how much each feature contributes. Figure size, we'll just make it a fixed size. Let's make it 6,4. Okay. Size 6,4. PLT the bar. Make a bar plot. Since we have 23 features, let's make it range 22. Range 22. PCA variance. So we're plotting our variance, right? PLT dot show. Okay, what's the error? Fixed size is equals to. Perfect. Now that we have our variance, we can also let me label the plot so that it's clear. So we can say PLT dot y label. So our y label is our variance. Remember, this is the variance ratio. Our variance, and we have PLT dot x label, and our x label is our features or our components. Right. Let's see. Perfect. Now that we see each contribution, what we can do now is, okay, we have 23 features. Let's bring it down to, let's reduce down our features. So we can say PCA. Since we already have PCA, let's call this one PCA2 or PCA1. Okay, PCA2 will do. PCA, the same thing we did before, PCA. But now we're talking about number of components. Components is equals to, say, 17. And we have PCA2. Now we fit all the X features. Fit the features into the model. Fit features. X features. And we'll have our 3D plot. Just call it X3D. 3D features is supposed to please CA2 dot, let's transform our features X features. Okay, PCA2. So now what we want to do from here is plot a scatter plot. So we want to see how much this. We want to see the variance distribution. Let's see how we plot it. PLT dot figure. It's equals to fixed size. So we'll use the same figure size, fixed size. It's equals to 6. PLT scatter. We plotting. range. Let's make it 0, comma, make it 5, x3d, comma 5. So now here we just want to see how each feature contributes to the overall model. Define a class data file, data file, plant data file, class, right? PLT shell. So we have our PCA2 number of components 17, X features, and you transform our X features to PCA2. Fig size 64. Scatter. Okay. Transform. Let's see. Great. Okay, this is what we have now. Okay. So this is basically the distribution of all features, or rather the variance of each component within our data set. So what we can do now is we can do the same thing we did here, and reduce the number of features. See how that affects the entire model. Let's take it down to 2 features and see what happens. 2 features from 0. Since we have 2 features, let's put it down to 1 here. Let's see what happens if much changes. You see here we have, okay, let's go. Yeah, perfect. You see now we only have 2 components and still it hasn't affected not much information has been affected in our model. So the variance is still slightly okay. Yeah, perfect. So yeah, this is basically how PCA works. And now we reduced our model from 23 features to 2 components.